So the experimental evidence for bonding will come from quite a few experiments that you probably won't be able to do in every school. The first one's probably the most important, and you can do mostly with balloons. So you can create a negative charge with the balloon, and then you can cause induction. So you can bend water because the negatively charged will induce a positive negative charge in the water, or it will cause another balloon to be attracted to it. But if you can get both of them to be the same, so if you charge both balloons up, they'll repel each other, or with the electrograph here you can see these ones here are both positive, and so they repel. So positive is attracted to negative. So that is the basis of chemistry, positive attract to neg. So we're going to base it on that. And for science, it's based on experimental evidence. So we'll do the experimental evidence first, and then we'll go to pos versus neg. You can also graph the distance versus static charge, so the amount of piece of paper that get picked up, and you'll see that, as with all forces, it's exponential. So the distance massively reduces the force. So distance is far more important than the size of the force, which will become relevant if you look at some combinations in more detail. The other thing you can do is check that electrons are in set energy levels. You can just look at the hydrogen because it's only got one electron, put it through a spectrophotometer. You can see that the energy levels are there. They're the colors that indicate how much energy there are, and they're in set levels. And that also matches with the mathematical modeling here, which you can also simulate those subshells by finding the standing waves, which is when the stability of it. So if you just get a ring and play around with the frequency until you find where the standing waves are, and they will match the SPDF, which is the actual real thing that's the three-dimensional shapes. But we're just dealing with a simple pos-neg explanation, so we're just going to stick with the crude electron shells, and so we'll just also be a little bit more crude there and just say it's first, second and third shell, the different lines, even though we know it's a bit more complicated from SPDFs. So moving on from there, the first one are the noble gases. So they have everything you want. They have the wave stability, so they have the correct number of electrons in each shell, so they don't want to gain or lose electrons. And they also have the electrical stability, so they have the same number of protons and electrons. Now, most elements will end up trying to get wave stability, and so they'll deal with the fact that they'll have an uneven number of electrons, so too many electrons negative, not enough positive, in order to get the wave stability. But because noble gases meet both of those, they won't react because they've got everything they want. Okay. And so moving on to the first one, I think it's the most logical to do metallic. So if you go to the left-hand side of the periodic table, there is a very small number of protons relative to the valence shell here compared to the right-hand side. So these, because it's not very positive, they are not going to have a very strong attraction to electrons that they're from the outside. And so what's going to happen is when you have these things by themselves or bound with each other, they have very strong attraction, a very weak attraction to the electrons on the outside. So we call that cations floating in a sea of electrons. And so the electrons are free to move. And so that is metallic bonding. It can be bent, and because of that fact that it's not as strong. Now, relatively speaking, if you go to the right-hand side, there are far more protons in the nucleus compared to the distance to the valence shell. So they have a much better ability to hold on to and attract electrons from somewhere else. So when they form elements with themselves or with other guys in this group, the electrons are more tightly held, so they're trapped in between the two nuclei. And so they form covalent, what we call covalent bonds, molecular bonds, because the electrons are trapped in between. When you combine the two of them, if you have these ones that don't have a strong nuclear charge, a strong number of protons, highly positive, they will be stolen by these guys. So I'm just keeping it simple now by keeping them both at the same distance here. So I'm just comparing this with this one. If you want to do a more complex comparison, you'd consider more complex ideas such as 4 equals 1 d squared, etc. So generally the electron, to simplify it, we just often say the electron is stolen over here. Now because of that, this now the left hand side becomes pos, the right hand side becomes neg, and because positive attracted to negative, they still stick. Okay, so sometimes we're talking about positive from the inside attracted to negative electrons, and this one we're talking about the entire ion being positive and the entire ion here being negative, and so they stick for that reason. Okay, so they're the experiments, and hopefully that gives you a logical understanding of metallic covalent ionic bonding.